Welcome back. Uh, now, as you remember, we were going through the segmentation, image segmentation part of our course. We have up to now three different recordings, lectures. We have explained the techniques based on histograms, not considering any neighborhood information. Then we have moved to more sophisticated techniques, which is called spatial coherence-based techniques, simple algorithms such as the region grows or region merge. Then we moved to graph theory-based methods. In those approaches, we have seen the famous normalized cuts. Now, this is the fourth lecture for image segmentation part. And today I'm going to talk in a different approach. This approach is also very fundamental. Until now, in this course, we haven't used the concept of probability a lot. We considered many things as deterministic, and physics-based approaches we basically performed. But obviously, we can assume our intensities and some unknown labels, unknown parameters to be random variables. And then we can move in this direction. Today, in the next about hopefully 50 minutes, I'm going to try to explain the concepts, how to apply probability theory to image segmentation problem. In fact, we have already started dealing with this in the last lecture, a technique called mean shift, which was assuming the data pixels are coming from a distribution. We are trying to find the modes and every pixel belonging to different modes. In this way, we are assuming or we are performing the segmentation. Now, today, we will move further. We will try to include again, the neighborhoodness concept with the assumption of probabilistic modeling together. This is called probabilistic graphical model-based approaches, and something called Markov random fields that I'm going to try to explain next is the fundamental approach for solving those kind of models. Before moving into that, I would like to remind you that this concept can be applicable to not only segmentation, optic flow, stereo estimation. In many different parts of vision research, people can use Markov random fields. Let's look at the main steps. First of all, I'm trying to make segmentation of every pixel, and I'm going to assume that there is a label field. In other words, a label field which is giving some integer numbers for different objects. This is unknown, and I'm going to assume that that is random. That's a random field. In other words, a group of random variables with integer values. For the first object, the pixels will be 1, 1, 1. For the second object, 2, 2, 2. Okay? And this is assumed to be random. And we are observing intensities, colors or gray levels, whatever. We are assuming that they are also random variables. And the segmentation labels, the object numbers, are nothing but their conditioning events. Okay? Now, we're trying to estimate the labels after observing the intensities. That's logical. We have an image, we observe it, and there's the unknown labels. And those unknown labels we will try to estimate through these intensities. This is the first of all, the main steps. And maybe after some point, after some slides, there will be too much math. You will maybe forget these concepts. But the main thing is, I'm trying to estimate labels. These labels are random variables. The only thing I have is an observation of image intensities, and they are conditioning on each other. In other words, I'm going to show you that every object, a banana object, is assumed to be, or more probable to be yellow, or the apple object more probable to be red. The idea is I am giving a condition on the labels, and based on this condition, a class conditional observation, a class conditional color is easy to model. But the problem is, we will do the reverse. We will ask, if I observe this color, what is the probability that it's an apple? Just like in pattern recognition we did. And another thing is, we will also consider the neighborhood concept in a way, a more structural way to model this, not random variable field. And the next slides will try to explain these concepts. I'm going to start with very simple toy examples. Let's assume we have 5 interacting variables, joint variables, what we call it. These are not observed to us. These are unknown. Now, there is a joint probabilistic relation between these 5 random variables, like this one. This is a joint random variable. Like just 5 pixels, they are 5 labels, okay? Now, the thing is, we are trying to find out what is the most likely state variable of x1. If I give you this joint variable of 5 dimensions, I'm just trying to observe what is the most likely thing, assuming x2, x3, x4, x5 are known to us. Can you find most likely, most probable, the probability of x1? Now, two probable, the reasonable choices. I can try to find the value of x1, which gives the maximum of this joint probability, okay, joint PDF. This is called the maximum a posteriori probability solution, okay? Therefore, I'm just maximizing a probability, and the x1 value is your solution. Another technique could be, we could marginalize all other variables, okay? In other words, marginalization is the process from obtaining a marginal PDF from joint PDF, just taking the sum of the other random variables, here x2, x3, x4, x5. You marginalize it, then you have a joint PDF. You take the mean or the maximum of this variable, okay? Therefore, this is the MMSE solution where you obtain a number again about x1. It's an average number, and that's giving us an information again. Therefore, obtaining a PDF, a joint PDF, is crucial for us. We can do many things with that. Therefore, in this aim, we are trying to find the joint PDF of the unknown labels. Obviously, since the observed random image intensities are also random variables, I will just try to obtain a joint of not only intensities but labels together. Okay, how to do it? Obviously, such a problem is very intractable when you have high dimensions, not 5, but if you have 500, it's making these things are quite difficult. To make these things tractable, we have to make some assumptions. One assumption is this. Now, let's assume we have this kind of random variables. For example, 5 is caused or completely controlled, determined by x4, another random variable, the neighboring one. 4 is controlled by 3. 3 is controlled by x2. x2 is x1. This is, we call it a Markov chain. x1 causes x2, x2 causes x3. It goes on like this. We denote this, we draw this relationship by using a graph, okay? Therefore, this graph saying that these random variables are related, and x5 is causing or controlling x4, it goes on, sorry, x4 is controlling x5, and it goes on like this. Therefore, this relationship, this graph shows us how random variables are related to each other. For images, assuming their intensities or labels are affecting each other, we can have such a graphical structure as well, so that we can model these neighborhood concepts between the random variables. Now, one little thing to note, this is the nothing but the a joint probability is written in terms of a conditional times probability of A. Okay, therefore this aim, this difficult aim of joint PDF of 5 random variables, you can simply write it in this form. Okay, you write everything as a conditioning thing, and Pure probability of x1 is written as x2, x3, x4, x5 is your new conditional thing, and x1 is conditioned on that. It's very trivial to show that this is equal to the left-hand side, okay? Now, if we continue like this, I can take this, and I can write 3, 4, 5, like this one, and x2 and x1 together as a conditioning here. If you write these things in an open form, these two is equal to this one, okay? This is very easy to show. You can play it by yourself. And you continue like that, and you reach to this point. Now, what do we have here? It is saying that probability of x1 times probability x2 given x1, x3 given x1, x2. And it goes on like this. Now, one interesting thing to note. At this point, I can make an assumption. The fourth pixel is being affected by 1, 2, 3, okay, but I can assume in images or in some other modalities, x3 is fully controlling x4, and we don't need x1 and x2. It could be, okay, because this is not a bad assumption. All the information being carried by x1 and x2 may be stored here. Therefore, based only looking to this condition, I can talk about this one. Now, this is called a modularity, and this is called the Markovian assumption, saying that I don't have to write x1 here. Writing x2 as a condition is enough. Therefore, I can have this joint PDF, which is something very difficult to draw or calculate, or whatever, estimate. I can write it in terms of these kind of only a first order conditional terms. Look at this one, x5. You don't have to say the values of x1, x2, x3 for it. We assume only knowing x4 value as a conditioning event, I can obtain the distribution of x5 random variable. Now, this complicated thing, by the help of this Markovian assumption, okay, we can obtain such a relatively easier formulation for this result. Okay, now the previous summations, like this one, which is quite difficult, in this way, we obtain relatively easy thing to obtain as a result to say anything about x1, for example. Now, the thing we have learned here is this. If you have Markovian property, your neighbor is sufficient for you to model your probabilistic distribution. Everything becomes much easier. Now, how can we move forward from this point on? Now, first of all, until now, everything was directed graphical models, like x1 random variable is causing x2. But in practice for images, two random variables or two pixels are side by side. No one is causing the other one. Both of them are affecting each other in both ways. Therefore, in directed graphs, we have the nodes as random variables, and the direction says parent-child relationship, like this one. And obviously, every node I is associated by a conditional PDF defined by all the parent nodes, Pi, okay? And we have such a structure, okay? Therefore, this is a conditional PDF, xi random variable with the condition of its parents, okay? Well, whatever the Pi is. This is shown in this way, okay? And the joint distributions are defined like this, okay? Please note here, as we have derived before in the slide, I obtain 1, 2, 2, 3, 3 given 4, 4 given 5. And that's what it says here, okay? The joint of the whole thing, 1 to n, it will be nothing but from xn, xn minus 1, xn minus 1, xn minus 2. It goes on like this. And the last one is probability of x1 itself. Okay, therefore, this is the formal way of generalizing it with n pixels neighboring each other, one-dimensional in a way. We have this kind of a conditional PDFs multiplying each other. And we show it like this, and we have the previous result. Now, undirected is, it could be possible that random variables are affecting in both ways. And we just basically use an undirected graph like this, and no arrows as you can see here. And the joint probability, we can still write it. These are random variables affecting themselves in both ways. But the concept is, if this is causing this and if this is causing that, what it's saying is, in terms of x3, x3 says, I am only being affected by x2, not x1. And the other way, x3 also says, I am being affected by 4, not 5. In both ways, x3 is being affected. Now, we can write the joint probability of this graph in these pairs, x1, x2, x2, x3, x3, x4, x4, x5. Okay? Now, this function, phi, x1, x2, is called the compatibility function. You can assume this is something like a joint of x1, x2, joint of x2, x3, kind of thing. And please note, we are still, just like before, just like writing these as multiplicative terms by the assumption of Markovian property, I can obtain the joint probability of these random variables by the multiplication of these pairs. Okay? Therefore, this time, this is undirected. And again, I was writing in terms of pair of first-order conditional random variables. This time, I'm writing something called compatibility functions, something similar to joint pair PDFs of pair random variables, which are side by side. I write them. Okay? This is how I obtain a joint probability for an undirected graphical model like an image. Okay? And hence, we will be after how can we write to the joint probability of 5 labels, of 5 pixels, in terms of the joint PDFs of the pair of the labels nearby. Okay, at this point I have to define something called cliques. A clique is a fully connected set of nodes like this. These three is cliques because they are fully connected as a graph. Everything is connected to each other. But this is not a clique because this is missing. They are not connected. This is not a clique. Okay, a maximum clique is the nodes. This is the maximum number of nodes without losing the clique property. This is a maximum clique. This is not a maximum clique because these two can go to a third one and obtain a larger clique. Therefore, this is the maximum clique. But I cannot go to the fourth one because this is missing. This is also missing between them. Therefore, these are missing. They are not having a 4 clique. The maximum clique of these things is 3. Now, what I'm going to use later, these kind of cliques will be our like pairs here. And in terms of these cliques, we will try to write the joint probability. Okay. Now, this is the point where I have to make a factorization. Until now, I did a factorization for directed graphs, conditional PDFs, for undirected graphs in terms of the compatibility functions. Now, in statistical physics, in statistical mechanics, to define the motion of the atoms as a lattice, people are come up with something called Hammersley-Clifford theorem, where the joint probability of the whole thing can be factorized. Factorized means multiplied in simple terms. These can be factorized as cliques of a graph. Okay. Therefore, what I'm saying is this: I have a graph, and there are some cliques inside it, and I am just writing the joint probability in terms of the cliques of this graph. Therefore, if a distribution consisting of many jointly random variables, if they have the Markov structure, if I assume the Markovian property, only neighboring pixels affect each other as an undirected graph, this theorem says it can be represented in a factored form. and if and only if. In other words, if something can be represented in a Markov factored form as cliques, then it should be a Markov structure. This is what it says. This is the joint PDF. This is the PDF of all the random variables, of all the labels, everything. It says you can write it multiplication of. This is the multiplication of the potential functions, like the compatibility functions, of the variables in the maximum clique. If you have 3 cliques, for example, and maximum cliques, these compatibility functions are in terms of those 3 random variables, and the values they obtain returns you a likelihood value, okay? And you just basically multiply them to obtain the joint PDF. This is the set of maximum cliques. This is a normalization constant so that the total thing is equal to 1. Okay. Now, until now, we talked about factorization. Okay. Therefore, in this way, if you have such a thing, okay, if you have such a thing, these are our pixels. What I'm saying is this. There are maximum cliques like this one. This is one clique. Okay. This is another clique. This is another clique. Okay. And this is another clique. I am saying that this random variable, 6 random variables like a PDF of x1, x6, I am writing them in terms of like the first one times the second one, the third one, the fourth one. And this is the first one, this is the second one, this is the third one, this is the fourth one. Okay, therefore, I am just writing the joint PDF in terms of this potential functions, compatibility functions. And I define it in terms of the maximum cliques. And by multiplying them, I obtain the joint PDF. If the joint PDF is factorizable, we call it, this is a Markov structured distribution. Okay. Now, until now, everything was toy examples. I was only having an X random variable. I don't know what it is. But now let's go to the images and the segmentation problem. We have 2 concepts, intensities and the labels. Intensities are random, labels are also random. But intensities are observed, labels are not observed. Labels are tried to be estimated. Now, how can I relate intensities to labels? At this point, I'm going to use another concept called hidden Markov models, where the hidden concept is the unknown concept, the unobserved concept, okay? For our problem, it is the label, object number. The observed thing is image intensities. Now, how they are related? Now, let's assume we have both things are random. Let's assume n pixels, capital N pixels, x1 to x capital N. And that x vector is the unknown state variables, the segmentation labels. And z1 to zn are the measured observation, our gray levels, okay, or colors, whatever, color indices. Now, the concept is this. I'm going to assume the labels, object IDs, the object information is controlling the color information. Remember the example, banana, apple? Therefore, what I'm saying is this. If you are a banana, you will be yellow. If you are an apple, you will be red. I am enforcing something. You have to be more probable to be yellow. You have to be more probable to be red. Therefore, by such a modeling, I can control easily the observed thing, and I can obtain a model about the observed thing much easier. Okay, I can just find I can learn the color of the bananas or apples, and then I can just obtain such a probabilistic model. Now, this probabilistic model is obviously using bias rule. I hope everyone remembers this fundamental concept very well. Probability of A given B is probability of B given A, probability of A divided by probability of B. This is simple bias rule in high school. Okay, this is the same thing I'm talking now. Now let's look at here. Let's look at here. Okay, therefore, right now what I'm saying is this. Now Z is the label. Sorry, Z is the observation. I think a few minutes ago I just said it wrong. This is the observation. This is the label. Therefore, this process is something we are trying to achieve, obviously. We will observe something. We will try to estimate this unknown. But let's look at here. This is the example of a banana and the apple. X is your observation. Okay, so X is your label, which is like banana here. Okay, you know the semantic object, and you know how its color is distributed. Okay, therefore this is something very easy to achieve. Now, and this is an a priori knowledge. This is an a priori knowledge about these random variables. Now, in the previous slides, I have already started working with these kind of concepts, like Hammersley-Clifford theorem, neighboring pixels or labels, how can I factorize them. I know a little bit how to deal with this part. This is the new part, and I'm realizing that by the help of the bias rule, I am obtaining the real unknown, the posterior distribution, giving the observations. I'm obtaining the posterior distribution in this way. Okay? Therefore, this pure probability of x given x is a prior probability about the unknown labels and pixel labels that I'm trying to estimate. This is the measurements I obtained through the pixels by the help of this kind of a formulation. This thing that I'm trying to estimate can be written in terms of two things. One of them is, as I have said, we have already worked upon these things. And the other one is, we can talk about this thing. But at this point, please note one little thing. This is not that simple. It is like Z1, Z2, Zn given x1, xn. Lots of random variables that we have. Okay, this is quite complicated. Now, how can I obtain it in a simple way? Let's look at the problem. For directed graphs, I can assume the state, the unknown label, is the only factor affecting the corresponding pixel's color. Okay? Therefore, pixel 1 label controls, causes the color of pixel 1, Z1. It says the next one doesn't affect this one. Maybe your next pixel is a banana. Therefore, the label of banana should not affect the color of apple. Therefore, we have such a relation. The intensities, the colors are only affected by the corresponding unknown labels. But the labels can themselves affect each other. This is a directed graph, but in practice, if it is a directed graph, I can write this whole thing in terms of such a relation. How can I write this complicated thing or this complicated thing here in terms of such a simple first order terms? The whole thing I have explained until now, this conditional independence between Z1 and Z2. Knowing this X1, these are not related to each other. We say that Z1 and Z2 are conditionally independent of each other with these conditions of X1 and X2. Okay? Therefore, this conditional independence makes this joint can be written in terms of multiplicative terms of these first order, only one pixel label, one pixel color conditional PDFs. I just multiply them to obtain this very difficult joint probability. This is for directed graph. Images are undirected. I'm writing the whole thing similarly in terms of our compatibility functions or our the energy terms that we have. Please note this xn means here for xi, which is observing or knowing that it is labeled xi, apple, probability of observing a color, something similar to red, okay, for example. The multiplication of these things are giving us our joint PDF. Now, what is hidden? Labels are hidden. We don't know X. What is Markovian? Labels are also Markovian. Only your immediate neighbor affect you. The other ones don't affect you. Also conditional independence, so that you simply multiply them in a simple way, just like here, due to this conditional independence. Okay, Z1, Z2, Z3, they are conditionally independent of each other. If you know their states as a condition, they are not depending on each other. Now, hidden Markov model is a very general topic. It could have applied to many things in engineering, in electrical engineering, like speech recognition or whatever. There are three canonical fundamental problems. Okay, the first thing is how do you evaluate your observation probability? Okay, in other words, you observe a pixel as red. How do you give your probability? Now, please note that we really don't know. This red is due to the banana, which is observed in maybe a red illumination or a really red apple. We just simply obtain such a summation for every different label that you can have. Apple, banana, you try. Probability of being apple and knowing that you are an apple, what is the probability of observing red, plus knowing that you are a, I don't know, orange, knowing what's the probability of being an orange, and knowing that you are an orange, what is the probability of observing red, kind of. This is how you obtain a mixture probability. This is how you are evaluating. As soon as I observe, as soon as I observe a red color, I know that this reason, the probability of observing is this due to this concept. Okay. Now the second thing is more related to us. I would like to obtain this thing. Observing colors of all the random variables, what is the probability of their labels? Okay. And maybe I'm gonna maximize this thing with respect to X, and I'm gonna give you an estimate, which will be your maximum a posteriori estimation. Why a posteriori? Because this is an a posteriori probability. I write it in terms of our likelihood times the a priori probability. Therefore, this is our map estimation. In fact, in this chapter, what we are doing is always this part. Okay, observing colors, observing an image, observing pixels. We are saying the labels, the joint probability of the labels. We maximize it, and we say that, hey, the labels should be 1, 2, 3, 4, 5. These are the labels of the pixels. This is my segmentation result, and I'm going to obtain it through this map estimation process. I don't know the P. I'm trying to explain you right now how to obtain this very complicated P. And this is our bias rule that I have already explained in terms of the model parameters. And please note, I have to also estimate the parameters of the models. If you are going in this direction, there should be a way to find this optimal parameters from some training data, by somehow a prior knowledge. You have to give me apple is red, banana is yellow. You have to know this so that you have a model. Okay, and then this is how you do it, because if you know these probabilities using maximum likelihood estimation, you can say that, hey, if I'm observing this pixel red, this pixel red, this pixel yellow, hey, this should be due to these parameter sets to jointly maximize this problem. Okay, this is our hidden Markov models, and now let's see how do we obtain this Markov models on the graphs. Okay, Hammersley-Clifford theorem says this time it gives a specific probability distribution called Gibbs, a statistical mechanical physician called Gibbs. This is the joint PDF written in terms of FC of X, and the C is defined on your clicks, okay? And that's an exponential, okay? Therefore, I'm saying that Gibbs distribution means this is like e to the minus an energy function of X, okay? This is like this. This is the normalization term in front to make everything sum up to 1. And that energy is obtained. This is a multiplicative term, exponential multiplicative terms. Therefore, in the exponent, there will be summations, okay? If you have these terms obtained like multiplications, therefore, that should be in terms of the summations of these terms here. Obviously, the same clicks. Now, I converted my problem such a way. There is an energy function, we call it, okay, an energy function. That energy function is the exponent of the Gibbs, and that energy function in terms of sum of, since we are multiplying the probabilities in a factorized form, we are just summing the exponents using these energy terms, and those energy terms are defined within the clicks. Now, let me show an example. Ising model, something from physics, mechanical, statistical mechanics. Okay, assume we have a single parameter, gamma. Our model is this. We have x1, x2, x3, okay? Every pixel has a label, unknown. 0 or 1, binary. 2 labels, foreground, background. Object 1, object 2, or object 0, object 1. Now what I'm saying is this. Assume my energy function is like that. Between neighbors, neighboring pixels, you simply take their absolute difference. Multiply with a gamma. Now, if two labels are equal to each other, it will be 0, 0, 0, or 1, 1. Otherwise, it will be gamma. And this gives you either 0 or gamma. If your neighbors are same, you will obtain a 0, and you will obtain a gamma if you are different. Assume this is a distribution of x1, x2, x3, all the pixels. Now, let's have some random selections from such a large pixels or random variable set. Okay? Let's assume these are x1, x2, xi, and let's take a sample from this distribution. This is a probability distribution. It will give more likely samples for us. Hi, by the way, taking a sample from such a distribution is also a very difficult process. I'm not going to explain it right now mathematically. But let's assume I just obtain a sample from this distribution. What does it look like? It should be an image. It should be consisting of binary terms 0 or 1. But what does it look like? 2 or 3 examples. When your gamma is 0.5, when your gamma is 0.7, when your gamma is 0.8. What do we see here? What do we see here is this. When your gamma, when your penalty is small, the pixels are free to change from their neighbors. They could have a little black here, all the neighbors are white. You don't care about it too much. But as soon as your gamma is increasing, which means any neighboring value different from each other will hurt you with 0.8. Now, a typical sample from such a distribution becomes more blobby, more regions, dense regions connected to each other, just like here, okay? And for here, it's more noisy. What is controlling this? Gamma. Gamma is the parameter saying that you observe typical objects during your segmentation like this or during like that. I'm gonna use this kind of a model for my prior model about the objects, not the color values. This will be one object, banana. This will be apple. This is the a priori term, which will help me to find the posterior result. This a priori term is basically giving us nothing but how neighboring labels behave. Okay? This is how I'm gonna use this concept while I'm solving my segmentation problem. Okay, now hidden Markov models. Let's put everything together into the picture. Observed, unobserved. Unobserved is labels, hidden. Observed is the color intensities. Now I'm gonna have a Markov random field. It will be consisting of Gibbs distribution. Gibbs distribution is energies which are written in terms of summation of cliques. Okay, now let's have this. This is the label that I have about the structured labels, okay, hidden. These are the zi's, conditioning of xi's. They are conditionally independent of each other. Now let's combine them together. That was the thing I'm after. Observing colors of all the images, labels of all the pixels are estimated. I write it in terms of two terms using bias rule. And this is our, hopefully, the Gibbs distribution. Okay, this will be nothing but Gibbs distribution I have explained. It could be different things as well. Now, this is the term I'm writing, and that exponential, this is Gibbsian. This energy term has two terms. This term is only consisting of the things interacting between themselves. Okay, in other words, due to this one. This is due to this one. This is due to this one. Due to conditional independence, everything is scalars, single random variables. This is joint still. That joint is PDF, and that PDF is written in terms of nothing but the cliques. This is in terms of every pixel, one by one. You only consider their relation between each other. And at the end, my aim is maximizing this posterior probability for a Gibbs distribution, which is an exponential to the minus power. It will be minimizing the energy term. I'm going to minimize this cost function. That will be effectively, it's a maxima posterior estimate of my X unknown label field. And that is written in terms of this way. Two terms. This guy is here. That guy is there. These are our pair neighbors. Cliques of two. Maximum cliques here are just pairs. In this example, this is assuming 4 neighbor. If it is 8 neighbor, maybe 4 cliques could be written as well, but just 2 cliques right now. And now I'm gonna write apply. I'm gonna apply our hidden Markov random fields to image segmentation. Observed image, label parameter, model parameters, and X the unknown labels. Now this is our cost function. Now the concept is how can you write these things? Let's write some typical energy function. Let's start with this one. This is your, let's start with this one. This is your energy function, okay? The Ising model, okay? I think it's written Ising over this, Ising model. Now, this is your xi minus xj, again, labels, assume right now 2 labels, 2 observed, 2 segments, 2 objects. You simply make it binary. If they are equal to each other, gamma cost. If they are equal to each other, 0 cost. If they are different, gamma cost. Now let's look at here. I observed, this is due to this part. This is due to this part. I observed xi. Xi is apple. Apple has a histogram. The other one is also a histogram. And based on that, what I'm doing is I am just writing the corresponding histograms in this way, okay? Now, for example, an improved version is like that. you insert this one. If it is 0, you only consider this one. If it is 1, you only consider that one. Okay, therefore please note here, I am having two histograms. One of them is off. Okay, for example, this is off when it is x1 is equal to 1. You only consider the minus log, the histogram of the value. In other words, let me show it here. This is like a histogram. Okay, this is your HF. This is Z. This is your HF of Z. You observe ZI. You go there, you calculate this value. You take the minus log, typically less than 1. Therefore, that gives you this minus log HF of ZI is giving you, if it is a large number, okay, it will be a low probability. If it is equal to 0, ideal, it is nothing but probability equal to 1. And we are trying to minimize this thing here. I'm trying to minimize this thing. Therefore, by having such a term here, for example, here, the background probability of Zi is calculated minimum 0. We try to minimize it. If it is a large positive value, we will just try to make it smaller. Okay? Therefore, this is giving us, if this is apple, if the color is yellow, it will be a large number. If it is a perfect red apple, and if you give a red, that will be 0, which is minimization. Therefore, this term typically could be, sometimes you enforce something to be exactly equal to be some values. We can use such a thing in practice. And in real life also we use mixtures of Gaussians for the observed data. Therefore, what we are doing here is yi is, instead of z, we are having this y. This is just inserting the value y, knowing that you are coming from one particular class, okay? And that class probability is given just right here. Now, here, let's look at some extension to the Ising model. This, we call it prior term. The prior term can also be written like, instead of a gamma, we are just simply writing in terms of an exponential term. Just think about like that. There are two pixels neighboring each other. This is x1, this is x2. And one intensity is 100, the other one is 200. It looks as if they are really different from each other. Therefore, I shouldn't give too much cost for this, because maybe this is apple part, this is the banana part, and through here we shouldn't give too much cost here. The way we do it is, if you write it like 100 minus 200 here, okay, that will give you a small number, okay, and that small number will diminish this cost. This is a concept which is using the Z information. Previously I wasn't using Z here, but this time I'm using Z. Therefore, this is something called the conditional random field rather than Markov random field, but it requires some training to obtain these results. This is something more popular right now, but Markov random field is the fundamental concept behind it. Now, how to determine the map estimates for MRFs? This is the cost function. Until now, we will have many techniques in the last 30 years. One of the most simple ones or easy ones is this ICM, iterated conditional modes, okay? Now, what we do is, let me try to explain here. We find a place, xi, Okay, I'm trying to guess the label. I go and calculate this thing. Okay, just assuming everyone is fixed. These are fixed. Xi could take some labels like 0, 1, 2, n. Now what you do is you calculate your energy function in terms of these two terms. You calculate this, making all of them fixed. Just for every different value, you calculate this energy function. In other words, x1 energy is 0.3, x2, x1 is xi is equal to 1, xi is equal to 2, xi is equal to n. You calculate your energy function, and whatever the minimum one you are trying to minimize, you say, okay, whatever the initial value of this thing, I am just writing value of n here, and I go to another random place and I do the same thing. I go to another random place. I continue like this. A very local approach, but one by one you are minimizing your energy term by trying all the labels. This is local, no guarantee for a global minimum. This is certainly suboptimal. Okay, simulated annealing is a famous approach, which is stochastic approach, which is used in statistical physics. And here we basically not every time minimize it. Sometimes we try to increase our cost as well in the initial stages of your iterations, but that is guaranteed to converge, but it's a much slower algorithm. Then there's the algorithm of belief propagation. As for some time it was working good, but no proof or no guarantee for optimal solution. And for min cut max flow algorithm, we have a solution for optimal result, a guarantee for the optimal xi's, and for binary problems, let's be careful on this. In other words, this is not a binary problem. This is n labels, but if your xi is only having 1 and or 0 and 1, this is a binary problem. If your problem is binary, foreground, background object, then it can be shown that an algorithm called min cut max flow can minimize this, such a term, such a Gibbs energy function, optimal way, guaranteed to converge to the minimum optimum. Okay, therefore this algorithm is called min cut max flow. That's an interesting algorithm. I'm gonna briefly try to explain it next. Okay, therefore let's summarize what we did. We have a cost function to be minimized, the exponent of a Gibbs distribution. Gibbs distribution tried to maximize, this is tried to be minimized, and this minimization, it's difficult because lots of random variables. 1 million pixels, we are talking about 1 million labels unknown, okay? And we are trying to estimate them together. ICM does it pixel by pixel, optimizes pixel by pixel and repeated many times. Unfortunately, nothing guaranteed for a global minimum. The cost function is not minimized well. But this min cut max flow, more famous name is called GRAPHICAL, is guarantees to obtain this binary labeling in an optimal way. Now let's see, how do you minimize MRF energy using min cut? Now assume it's a binary labeling problem. Two random variables, just 2 pixels to explain it easily. This is our the prior term, binary term. This is the prior term here only in terms of xi and xj. Okay, they are neighboring relations here. This is the terms which is consisting of single labels. This is the term that's controlling the color of the object, okay? Now, please note, for 2 pixels, you can have the first pixel energy, okay? The second pixel's energy, and between 1 and 2, we have this term. Once again, this is between the clicks, okay? Okay? This is for every pixels, we have the in relation between the label and the color, okay? And this is the 2 pixel relation that we have. We are trying to minimize this energy, okay? And we convert the problem into the graph with 2 extra nodes. Now, how do we do that? These are 2 pixels. I insert 2 nodes, S and T. S is foreground, this is for background. This is for object 1, this is for object 2. Now, what I'm going to do is this. This cost function, this term will be written here as an edge. Now, and if my pixel is, both of them are belonging to the foreground, for example, I'm going to write their cost to here and here. If they belong to background, foreground, it will be written here to here. And I'm going to have all the things, all possibilities written in the edges of this extended graph with 2 extra nodes. Okay, repeating once again, 2 pixels, 2 extra nodes. This is a binary problem. And I write all these single terms, all the possibilities here. What is this possibility? Pixel 1 belongs to here, pixel 1 belongs to here. Pixel 2 belongs to pixel 2 belongs to here, pixel 2 belongs to here. And their costs and their values being different, 0, 1, 1, 0, they should be equal to each other to be able to do it. This one 1, 0 and this one 1, 0 should be equal to each other, their cost. If you have this, now look at the result. Assume these 2 are belonging to here. You obtain the cost, okay? You obtain the cost. In other words, this is belong to here. Therefore, which means you write the cost of not being in the other way inside here. And you write of this one not belonging to this one as a cost to here. Therefore, the sum of these two equal to this energy is giving us our total cost. The other way, this belongs to here, that belongs to there, okay? These 2 are 2 is belonging to S, this is belonging to here. Therefore, the cost of being belonging to here is written this one. The cost of belonging to there is written to this one. Therefore, this belonging to T written here as a cost, okay? And that belonging to here written as a cost here. And since they are belonging to 2 different objects, object 1 and 2, there is a cost of being different, and that is written here. This cut, consisting of this one, and that one, is sum of the 3 energy terms that I have. And similarly this one. What I'm trying to explain is this. I have a energy term to be minimized by adding 2 extra nodes and connecting every pixel to these nodes. I realize that the cuts, which is cutting the graph of T from another subgraph of S, is giving me all the combinations, and I can write the corresponding energy terms to the cut values. For a multiple thing like that, 9 pixels, their relations are written in the yellow ones. 9 pixels, their relations between them, their label differences or similarities are written here. Now, whether this P belongs to this one or to that one is written in the red or the blue ones. Okay? And what I'm saying is this. At any instant, assuming this one, those ones, red ones belong to the source, and that one belongs to the blue. I can have, for example, I can cut this three-dimensional graph at some particular nodes. Now, cutting this blue, saying that this is belonging to the other one, and cutting them from here, saying that you belong to the red one, you belong to the blue one. And these cuts, some of these edges are giving you nothing but this cost value. Let's be more precise. The edge between P and Q, the yellow one, you write the weight as B here, okay? And this is showing us how different they are, okay? We write the between edge P and Q, we simply write the yellow one, which is if they have the same label 0, if they have different label, a cost like B over there, okay? Now, P and S, this one, S and P. Now, what I'm writing is this. If P belongs to this, P belongs to the capital P, okay, and P is not an object, okay. What I'm saying is this: I am not sure whether this is definitely belonging to the object or the background. This is not the element of object or background. This one is prior given by the user or by some prior knowledge. This is the thing that I'm trying to estimate. What I'm saying is this. I'm gonna write a background cost multiplied with a lambda. If this P is not belonging for sure either object or the background, okay? Therefore, I give the cost P, PR, lambda R, assuming this is the background, okay? And if I write it to here, okay? Now, similarly, I write the object cost when you have this thing to here. Now, these two are for this purpose. If P is, by some reason, a priori knowledge, user interaction, is known to belong to background, you give zero cost. S is background, okay? Therefore, you give zero cost to it, and this means certainly P, you write it here, for example, background. Or another Q is belonging to object, you write here zero cost. Obviously, we are trying to minimize this. Zero costs are preferable. You are enforcing them to get those values. Okay. Now, K is you are giving the maximum cost that you can have in your problem. And if you know that this P belongs to the background, you give the maximum cost to the object. In other words, this is 0, that's the maximum. If, for example, this is 0, the other one is the maximum. You are enforcing 0 for one of it, maximum for the other one. Once again, these are for some pixels, maybe some a priori knowledge, user interaction, you fix them. You don't estimate them. You say that I know that you belong to these objects. This is for those pixels. For the others, you simply write our cost functions. This cost function here, okay? Now, this is how we fill our cost. Then what we are realizing is this. We are trying to find a minimum cut. A cut, the green cut here. That green cut will just be nothing but the sum of the energies here, and those energies will give us our nothing but the minimizing energy term here. Therefore, I converted my problem into a minimum cut maximum flow equivalence theorem. What is that? I am trying to push some water from here, and the cost values are our capacities of the pipes that will make the flow reaching to here. My aim is trying to push the maximum flow of water from here to here through these pipes, and the costs are controlling them, determining how much maximum flow you can obtain. We can say that the pipes with the minimum capacity will determine the maximum flow going to the other side. Okay? And that will be controlling the whole thing right here. Okay? Now, the max flow, how do you go and push the maximum amount of flow to the other side, is obtained by something called augmenting paths algorithm. Okay? We start pushing water from here. I'm going to explain in the next slide easily. And I'm going to just push as much as water from here to here. If I push, for example, 100 water, you cannot push it from here. It's 90 here. If you push 60, it will pass from here, that will pass from here, but it cannot pass from here. Okay? Because this is the maximum capacity. If you push 50 from here, water amount, 50, 50, 50, it will pass it. But obviously, when you push 60, it can be divided in two parts, 60 and 30 here, and it can continue from there. Therefore, at some point, such a system will be in an equilibrium. You cannot push more water based on the capacities. And what we are saying that is this. At some point, the pipe capacities with the smaller amount will basically control the amount of water flowing from one side to the other side. Okay? Now, if you look at here, for example, this part, 60, 30, 30, sum is 120. And that is saying that from left to right, the maximum amount that you can push is 120. Okay? You cannot push something larger than this one. This is beyond our capacity. And this, the bottleneck, minimum cut, is our solution, optimal solution to our minimization. Okay, let's look at the algorithm. Find the shortest path on unsaturated edge of the graph, push maximum available flow through from this path, and iterate. Let's do it with an example. Let's start. Push some water, okay, and you push, 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 you get to the maximum, okay. Now, some of the edges are saturated. For example, this one. This one is saturated, you cannot obtain more. But these are unsaturated. They have larger capacity. I mean, the thickness of the lines show the capacity. These are larger, these are smaller. Now, continue to push. You cannot push because it's saturated. Now, you go to the next path. You push, push, push. You increase the flow. You continue like this. And after some point, you cannot push water anywhere, and everything is maximum. And now I have to find a cut, and the capacities of these things will give me nothing but our maximum flow from one side to the other side, controlled by the capacities of the bottlenecks with the minimum capacities. But those pipes should cut one side from the other side. Where is that cut? You reach the maximum flow. The capacity of this guy, the capacity of this guy, the capacity of this guy, and the capacity of this guy, they are fully utilized. Their sum is the maximum flow. And those terms are our terms, which gives you minimum energy of our cost function. And those are the labels that I have to select for my pixels. One interesting thing to note, I'm just stopping, this is the last slide. Everything was binary. How can you extend it to multi-class? We call it alpha expansion move, which is nothing but the application of this optimal algorithm to multiple labels. If you have multiple labels, not 2 nodes, you put k nodes, 1, 2, 3. You fill the edges, just I have explained before. And the way you do it, you again, this is one of them. One of them is 1. All the others at the second one. Now the problem becomes 2 label problem. Red versus the green. Binary problem. I solve this problem. Now in this way, I randomly select one of the labels, and I obtain, and the remaining one, the other labels. I obtain an optimal binary segmentation. And such a division, if it makes an energy decrease, we accept it, otherwise we decline it. We randomly continue in this way. Okay, let me finish as a summary. This concept is not for only image segmentation, optic flow, many things you can do it. About images, you can model it using Markov random fields. A Gibbs energy is minimized to obtain this unknown segmentation labels. Gibbs energy requires minimization of some random variables jointly connected to each other. We do it in an optimal way and with an algorithm called GraphCal. This is called the algorithm called famous GraphCal algorithm. I realized that I didn't write anywhere GraphCal. But this min cut max flow, the GraphCal algorithm, is the optimal way of solving binary problems. And sometimes we need some initial model parameters. At that point, we need some user interaction or some other prior information. And that's how we solve image segments using probabilistic models. Okay, that concludes our problems. This is the extra, which we are not responsible for the exams. Thank you.